So Julie Rowlett from Chalmers University does geometric analysis. Thanks so much.
Thank you, and thank you very much to the organizers for inviting me to talk here. And thank you to all the other speakers for the great talks so far. So, I guess I have giant chalk. All right, so the title of my talk is Geometric Analysis, which is pretty broad. And what I want to focus on today is basically the following, a particular perspective of the following question. So the question is, how do geometric features affect physics? And mathematically, I'm going to interpret physics as analysis. So at some point, I realized that physics, a lot of physics, is basically just math with cooler words. So you can translate a lot of physics into math into just different words. Like, a good example is a hyperkähler 4 manifold in physics would be a gravitational instanton. I think that sounds a lot cooler. So, as a nice warm-up, since everybody just had lunch, my introduction is going to be via an example, a very basic example. And this is actually, no joke, this is the first problem on my students' exam in Fourier analysis, my bachelor's students in Fourier analysis. This is their first exam problem. I just started grading it. They're doing pretty well. So, okay, so what we see here is a homogeneous heat equation with L2 initial condition at t equals 0, with the Dirichlet boundary condition at x equals 0. So this is the initial value problem for the homogeneous heat equation on a half-line. Okay? So to solve it, what should we do? Hint, the course that the students are having an exam in is called Fourier analysis, so yeah, so we should extend the function f either evenly or oddly. Which way? Oddly, yes, Pierre. So to solve this, we extend f oddly to r. Take the Fourier transform. The whole PDE in x, of course. And then you'll end up with an ordinary differential equation in t for the Fourier transform of the solution. You solve it. You write everything back in terms of the initial function, and you're going to get that u of tx will be the integral from 0 to infinity f of y times e to the minus x minus y squared over 4t minus divide this all by the square root of 4 pi t. Okay? Now, in my class, if you remember this being the heat kernel for a half-line with the Dirichlet boundary condition, and you just slap that on as your answer, this expression, and you get it perfectly right, you get a full 10 out of 10 on the problem. So this is the heat kernel, which is the Schwartz kernel of the fundamental solution of the heat equation for the half-line with the Dirichlet boundary condition. Okay, and I'm going to give it a name now. We're going to call it H of T, X, Y. Okay? So, the heat trace can reveal geometric features. So let me give you a little example. The heat kernel on the real line so no boundary condition, just looks like this guy. So I'm going to write it H sub R. Okay. And it is this exact expression. And so, for example, so taking the trace means setting x equal to y and integrating. So for example, if we integrate from A to B, the heat kernel for the real line, setting x and y equal, we get the length of the integral over the length of the interval over which we integrated. So we see that geometric information. Okay? Okay. So now let's look at what happens if we integrate the heat kernel for the half-line. All right, so throughout my talk, because this is like an introductory workshop kind of thing, I sprinkled in exercises so that those of you who are really interested can then go home and work on the exercises, or do it this afternoon, and I'm around all afternoon, so if you get stuck, you can even ask for help. Okay, so first exercise. Show that if A is greater than 0, then, so I called my heat kernel for the half space just H, okay? Then if we integrate from A to B, H of Txx dx, what we get is the exact same thing, plus a remainder, and the remainder satisfies the following estimate. It's rapidly decaying as t goes to 0. So in particular, it decays faster than any polynomial in t. Now, exercise 2 is to compute the following, or show that, because I computed it. When we integrate close to 0, my heat kernel for the half line along the diagonal, this is what we get. We get the same length of the interval that we integrate over kind of term. Then we get something else. So this is the complementary error function. So for any epsilon greater than 0, this trace of my heat kernel picks up this extra minus a quarter. No matter how tiny of an interval near 0 you integrate over, you're always getting this minus a quarter. So it's like the heat trace feels that boundary. And by the way, ERF C of epsilon over square root of t also satisfies this very, very quick decay as t goes to 0 for any epsilon greater than 0. Okay? So in this sense, my heat trace feels the boundary, or I'll think of it as a corner, okay? It feels this point in the sense that we pick up this extra 1/4, which we always get, no matter how small epsilon is, okay? All right. So we could also do this. This will be another exercise. So for the Neumann boundary condition, exercise number 3, so that's just requiring the derivative to be 0 rather than the function to be 0, which corresponds physically to an insulated boundary. That the same calculation will be, you get the same first term, and then you get plus 1/4, and then minus the ERF C term. It'll be the same as Neumann, at least the leading part. Because Robin is sort of like Neumann up to leading order. Yeah. Okay. So that was our warm-up. Now, I want to get into the focus of this talk. So the focus of this talk will be the heat kernel and its trace, and investigating what geometric information we can extract from that on curvilinear polygonal domains. And this is based on joint work with my mathematical brother, David Schur. And if he was my PhD student, then he's my mathematical son, met at Nursultanov, but that feels weird. My PhD student who's now starting a postdoc in Sydney, met at Nursultanov. It's the preprint that you can find on the archive. So, all right, so let me explain what we're going to be looking at. So here's the geometric picture. Now we can do this in surfaces too, but for the sake of simplicity, I'm just going to talk about domains in the plane, okay? So some of the interesting features are that my corners do not have to be actually straight corners. They can be just sort of asymptotically straight. I just have to be able to define an angle, so I cannot have any sort of a cuspy-like thing, okay? Okay, so, and then I want to consider in this work, we want to allow Dirichlet, or we do allow, Neumann and Robin boundary conditions. And we want to allow all three of them. So for example, we could have, in this talk though, I'm just going to focus on Dirichlet and Neumann. So we could have, for example, Neumann over here. And that requires the normal derivative to vanish. Okay, so I'll write that. du dn at the boundary, piece 0. And we could have right next to it right up next to it, we could have, say, right here, Dirichlet, which requires the function to be 0 at the boundary. Okay? So we can have any sort of combination of Dirichlet, Neumann, and Robin we want, but I'm going to focus on just Dirichlet and Neumann for the sake of simplicity. Okay, so my heat equation is now in my geometric setting is now 2 dimensions. So my heat equation is going to look like this. Ut plus Laplace u is 0. And don't panic, because this is my sign convention. It's minus dxx minus dyyy. Okay? So that's our homogeneous heat equation. And now we have a few challenges. Well, the first one is we can't write down an expression for the heat kernel. We can't do like we did over here. That's impossible for that funky thing. So we have no explicit expression. Oh, and let me give my domain a name. I'm going to call it M for the heat kernel, which will be the Schwartz kernel of the fundamental solution of the heat equation, analogous to our one-dimensional example, which I'm going to call HM. And now here, so in one dimension, you have the heat kernel depending upon time, and then 2 space variables, 2 individual space variables, so 2 copies. It lives on time and 1 copy of your geometric setting and a second copy of your geometric setting. So here it's going to be a function of t, and I'll write z and z prime, where these are variables in R2, okay, because we're in the plane. Okay, so we have no expression for this guy. Ah, yikes. So how the heck are we going to obtain geometric information from it, or even take its trace, because we don't know what it is explicitly. So another issue is if we have, like in my picture, Dirichlet boundary condition. So there we're demanding this heat kernel has to vanish along that curved piece, and then right next to it, the normal derivative has to vanish. So it could be like not continuous, which is kind of bad. Mixed boundary conditions, HM might not be continuous at, say, corner points. So double yikes. Okay. This is such a weird system. It's so messy. So, having lived for many years in Germany and Sweden, I'm a big fan of the water system. We clean our boards sort of like you clean a car. You like wash it, and then you use like a squeegee thing to dry it. But this is working all right. All right, so our goal is nonetheless to obtain information about the geometry of M by computing somehow the heat trace, which here will look like we integrate over M our heat kernel, setting the 2 space variables equal. Okay? and in particular, how it behaves as t goes to 0. So let me give just a little bit of physical intuition for why this is reasonable. If you think about heat, well, the geometry where heat is should affect how the heat flows, right? And so we should sort of see it somehow. We should somehow see geometry, especially now over a long period of time. However, that probably won't be true, because over a long period of time, the heat just sort of spreads out, right? It just goes kind of everywhere. So any sort of geometric features, such as heat like clumping up somewhere or whatever, is going to be lost for long periods of time. So that's why there's some like physical intuition to hoping that like there could be some geometric information for a small time in here. So now, okay, so this is just, I'm going to review some sort of basic facts that we know. We do know some stuff about the heat kernel, and I'm just going to review those things here before we get into the microlocal analysis stuff. All right. So as in our example, the solution to the initial value problem dtu plus Laplace u is 0 in M. U satisfies whatever boundary condition we have, and u at time 0 is some decent function. To solve this, we integrate our initial data, t, z, z prime, times the heat kernel, just like in our one-dimensional example. Okay? There are, in this setting, eigenfunctions. Phi j, and eigenvalues, lambda j, for the Laplacian. So we have Laplace phi j is lambda j phi j, and our phis, I'm going to start at 1. So our lambdas go to infinity. They actually go to infinity kind of like j, up to a constant. And our phis are orthonormal basis for L2 on M. And our heat kernel can be expressed in terms of these eigenfunctions. Like this. So, well, I told you we didn't have an explicit expression for the heat kernel, but now I'm writing one down. But yeah, it's still not really helpful because we cannot compute these lambdas. And we cannot compute these phis. So as an exercise, though, using this expression, you can write this integral in a different way, in particular as the sum of e to the minus lambda j times t. And just FYI, the collection of all of these lambdas is called the spectrum of the Laplacian on M. And so those numbers are important, and anything which is determined by those numbers is something called a spectral invariant. And so this quantity is obviously determined by these numbers, and so we see that the heat trace is a spectral invariant. Okay, so yeah, but we don't know what they are. Yes. The one thing that could be weird is if you choose the Robin parameter with like to be non-physical, the wrong sign. And then you could get like, these are all non-negative, and if you choose the wrong sign with Robin, I think you can get them. Some people's eigenvalues are all positive, but in any case, in the normally they're all of one sign, and if you choose the wrong Robin parameter, you could get them being of the other sign. I can refer to the exact part of my paper where we write that down explicitly. Yeah, so I can tell you that afterwards. Okay, so to achieve our goal, we want to do microlocal construction, or really study of HM. Okay, so HM, my heat kernel, is defined, or is a function, initially, on my time variable goes from 0 to infinity, and then my space variables live in 2 copies of my polygonal domain. Okay, this is where it's initially or a priori defined. But I'm going to use a little analogy. This is like a cage. So it's defined there, but HM is not happy there. Happy in the sense of being mathematically well behaved. Okay, so this is not the natural habitat, so to speak. Okay, so we want to make HM happy so that we can study it and understand it. Just like an animal, like if it's happy, we'll have a better time studying and understanding it. So what are we going to do to this cage? Blow it up. Exactly. We're going to make it bigger so that HM is happier roaming around in there. So so we want to make this more like HM's natural habitat, or even make it HM's natural habitat. So to make HM happy, we will blow up this space. Yeah. And thankfully, Xuen has already introduced a lot of the basics about blowing up. But I'm going to review it again, because it's, it takes a while for that stuff to sink in. So, yeah, so we're going to blow it up, and then it's going to making a bigger space. What we're going to call heat space, or double heat space, which will be denoted by MH2. as is, of course, tradition. Great. Are there any questions so far? Okay. So I'm going to just list initially everything that we're going to blow up, and then I'll explain like some of the heuristics of this. Yes. Yeah. Yeah. Yes, for positive time. I mean, it could be like discontinuous at corner points. So it will be well-defined up to the boundary everywhere except maybe at the corners. But it's well-defined as a distribution. Yeah. Any other questions? Okay. So this is what we need to blow up. In each copy of M, we need to blow up the vertices. And we will call the resulting space with all the vertices blown up M0. So let me draw a little picture of what that looks like. Okay, if I have a corner and I want to blow up a vertex, the vertex is just going to get replaced with a little segment. So you may think, well, this is still bad because you still have corners, right? The beauty of this, however, is that now if I had, say, Neumann boundary condition here and Dirichlet condition there, by blowing up the corner, my heat kernel can like transition between those two conditions, so it has a better chance of being well-behaved and happy with that corner, with more space in this corner now. Okay? So we do that in each of the copies of M over here to create, so this is the first part of creating my space MH2. The next set, so what I'm going to, and then I'm going to call HVRFJ is going to be M0 times Vj tilde. So the resulting thing, if this is Vj, meaning the jth vertex, then this face is Vj tilde. Okay, so this subset of M0 times M0 times 0 infinity, I'm calling HVRFJ. And HVLFJ will be the same, but in the other copy of M0. Okay. And then the next thing we do, the reason I introduced that notation, is we're going to blow up HVLFJ intersect HVRFJ. K. And this will create the new face, will be called HVFFJK. And now we're going to blow up HVFFJ, FFJJ, right, yeah. At t, I'll write it this way. I'm going to write square root t equals 0. So this means what's known as a parabolic in t blow up. Basically, the simple way to think about it is that you consider, I have to explain boundary defining function, but you consider your boundary defining function to be the square root of t rather than t. If this weirds you out, then just ignore it, okay? Just think of it as a usual blow up. And the next thing is the diagonal at the edges at t equals 0. So meaning the two space variables are the same, like z is z prime, at edges at t equals 0. Again, it's a parabolic one. And then finally, the interior diagonal. That's curve t equals 0. Okay, and this one, so I should write what these calls. This creates FFJ, creates SFJ, and this creates TD. All right, so what does blowing up mean? Let's just remind ourselves of that. Sort of. Side face? Yeah, the L and the F, or the L and the R stand for where the vertex face is. Is it in the left copy or the right copy? HV, I don't know. David has a reason for that. SF stands for side face, because we usually think of the vertex as being sort of in the middle and then the edges as being around it. TD stands for time diagonal. Yeah, so there are sort of meanings behind them. And FF, right, and that's why FF is like front face. So blowing up with that, the way you can understand it is you replace a set by its so-called inward pointing normal bundle. Okay, so what does that really look like? If you have a point S in your set, okay, then we're going to replace the point S by S theta, where theta is a direction in which we can approach S. Okay? So we can understand blowing up to a reasonable extent by just like counting dimensions. So in dimension n, we can blow up sets. They have to be, you can't just blow up anything willy-nilly. There's some technical assumptions and hypotheses or whatever about the sets. They have to be like piece of manifolds, blah, blah, blah. But we're going to just ignore that. And we're going to just think about the dimensions, okay? So we can blow up sets of dimensions 0, 1, and up to n minus 2, and the result will be something of dimension n minus 1. And so to give you a sense of how this works, let's think about the room. Okay, so we're in this room, which is three-dimensional space. Okay, so in the room, our n is 3. So I'm saying you can blow up things that have dimensions 0 or 1, and the result will be something with dimension 2. So let's start with something of dimension 1, like this edge. Okay? This edge is a one-dimensional thing. Now, I can approach the edge from three-dimensional space from this angle, that angle, blah, 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 blah. right? I can approach it from an angle going from 0 to, say, 2 pi. Okay, if my edge were, say, in the middle of the room. Okay? And so when I replace the edge with, now a point on the edge gets replaced by that point, and then all the directions that we could approach the point. And so how many dimensions do we end up with? The one dimension of the line, and then the one dimension of angles from which we can approach a point on the line. Does that make sense? Now, what about just a single point, like a single point in space? We can approach that by a whole sort of 2D set of directions. So when we blow up a point, then we end up with that whole two-dimensional set of directions in which we can approach the point. And so if you think about it like that, then to understand what happens with all these different blow-ups, see, like here, we take a vertex, and M has 2 dimensions. Vertex has 0 dimensions. So we blow it up, we get something one-dimensional. And then similarly, we can just count the dimensions of these different guys, and in our space, this thing has 5 dimensions. Okay? So that means we can blow up anything that has dimensions 0, 1, 2, or 3, but not things of dimension 4, because they're already of the maximal dimension. So for example, here, this intersection is 3D. And when we blow it up, we get something 4D. And then this intersection is also 3D. We blow it up, we get something 4D. The diagonal at the edges is something one-dimensional. And so that picks up a few more dimensions when we blow it up, and so forth. Okay? So having done all these blow-ups, we now have the resulting space, which I called MH2, which is like my sort of more natural habitat for my heat kernel to live on. Okay, so the next step is we want to study and understand the heat kernel roaming around this nice, cozier, natural habitat. So to do that, we will look at the different parts of this space, and we will use models, okay? So for each part, there are local asymptotic models. So let me give an example. So for example, for a smooth curved piece of a boundary away from the edges, if we zoom in really, really tiny, it's going to look flat, right? So for the edges away from the corners, I will use the model of half space, okay? And so we can write that model explicitly down. Dirichlet or Neumann. So this is xy, where y is greater than or equal to 0. That's my half space model. And so my heat kernel is going to be e to the minus x prime squared over 4t. So I have 2 copies of x and 2 copies of y. And then e to the minus y minus y prime squared over 4t minus plus. Minus is for d, plus is for n. That's why I wrote them that way. Okay, so this is my model. But I did all these funky blow-ups, and so I'm going to actually want to use different coordinates. So we blew up at x equals x prime, y equals y prime equals 0 equals root t. Now, when I described blowing up, I talked about angles, okay? But just take my advice. When you work with blow-up things, usually polar coordinates are, like, horrible. Okay, Rafe warned me of this, like, towards the beginning. He's like, "You're not going to want to do that. No, you're not going to want to use polar. No, try projective, try projective." And then, you realize, oh, yeah, I want to use projective coordinates. So after blowing up, new nice projective coordinates would look like, for example, big X is little x minus x prime over root t. Sorry, put these coordinates over here. And xc is y over root t. Xc prime is the same thing with the y prime. And then we have x prime and then capital T, which is square root t. And so then we can rewrite our model in these coordinates. Okay? And so my model is now big T to the minus 2, e to the minus capital X squared on 4, e to the minus c minus c prime squared on 4 minus plus e to the minus, add them. And then there's like a 4 pi. Right. Okay, so this is what I would call squiggly h sf comma 0. And so the way we will construct our heat kernel is like this. So we're going to, we would use local asymptotic models at all faces of MH2, which live at t equals 0, to write some j greater than or equal to 0, tj h face name, comma, j. And basically, the first approximation, or the first one, will solve the heat kernel, they'll solve the heat equation with some error. And then we try to get rid of the error. And so we sort of iteratively build this thing to solve the heat equation to infinite order at all faces at t equals 0. Now, there's a reason there's a 2 in the notation. There's a reason it's called MH2, and it's because to finally complete the construction and obtain the actual heat kernel, you need a triple space. And if you thought this 5-dimensional with all of these blow-up things was kind of complicated, the triple space has 2 copies of time, 3 copies of m, making it a, 8-dimensional thing. I mean, I guess the heat kernels will be happy in there because they have like a whole bunch of space to romp around in. But I want to skip that construction because it's kind of technical and it has a lot of blow-ups and whatever. But anyways, that's to finalize the construction, we would create a triple space and solve away the residual error term. But we don't need to do that because we can write down explicitly all of my leading order models. Okay? And we could write down explicitly the higher ones as well. Since we have those explicit expressions, we can use them to compute the result of our theorem. Which says that the heat trace looks like this. The first term is the area divided by 4 pi t. The second term is 1 over 8 times the square root of, no, I'm not going to have enough room for that. Times the square root of pi times t. And then I sum L of Ej. So these are edges where I don't have Dirichlet boundary condition. I have either Neumann or Robin. And then I subtract the ones that do have Dirichlet boundary condition. Okay, so these are the lengths of those edges. And then I'm going to have plus 1 over 2 pi, the sum of the Robin boundary conditions, the integral over that edge of the Robin parameter, and it continues. No, it has to be the physically correct one. The reason for that is we obtain our heat kernel explicit expressions using the inverse Laplace transform of the Green's function. And for the functional calculus, I can't have that spectrum over there. Like, they would, yeah. Maybe we could do it by other means, but we haven't thought about it. Okay, so plus the Euler characteristic divided by 6, which for something in the plane, it's just the number of holes, it's 1 minus the number of holes, so it has no holes, it's 1. If it has like a chunk taken out of it, then the Euler characteristic would be 0, and so forth. That's what that guy is. And here comes the part that I think is a little bit more interesting. Alpha j minus pi over 12 pi. So alpha j's are the angles at the corners. And then this guy, pi squared minus alpha j squared over 24 pi alpha j. And I'll tell you which these sets are. So this is going to be minus pi squared minus 2 alpha j squared over 48 pi alpha j, and then plus big O of root t log t for t going to 0. All right, so V equal is when you have a Dirichlet and a Dirichlet boundary condition, Neumann and a Neumann, or a Robin and a Robin. Doesn't have to be the same Robin, or a Neumann and a Robin next to each other, okay? And then the not, so this set are the edges where, or the vertices, sorry, where you have a Dirichlet next to a Neumann or a Dirichlet next to a Robin. Okay, so let's read off what our heat trace gives us. It gives us a whole bunch of geometric information. Well, maybe not a whole bunch, but yeah, a whole bunch, okay? So first of all, it tells us the area. Now, if we impose just the same boundary condition everywhere, we would just have one term, and when we added it all up, we would see the length of the boundary. Now, here we also see this integral of the Robin parameter if we have a Robin boundary condition. Here we pick up the topological information of the Euler characteristic. And here we pick up the fact that there are corners. So in particular, you never have this junk if your boundary is smooth. And so we can use that in as an application to prove the following sort of cute result. One can hear the corners of a drum. So our heat trace, remember, was equal to the sum of the eigenvalues of the Laplacian, well, e to the minus eigenvalues of the Laplacian times t. Okay? And there's this awesome paper by Mark Katz called Can One Hear the Shape of a Drum? And he asked the question, if two domains in the plane have the same set of lambdas, analogous to these lambdas, okay, those numbers are the same for the two domains, then are the two domains the same shape? So in other words, do these numbers determine the shape of the domain? And the answer is, of course, no. There was a paper by Gordon, Webb, and Wolpert, which was titled, One Cannot Hear the Shape of a Drum, right? So, okay, but those numbers, so they do pick up. So we say that quantities determined by the set, we say that they can be heard. And the reason for this is because if your domain were the face of a vibrating drum, these numbers would be exactly the resonant frequencies the drum would produce. And so with really good ears, you'd hear them all. And so you'd therefore hear everything determined by these lambda j's. And so the application of our result shows that these numbers pick up whether a bounded domain in the plane has corners or not. So in that sense, we are able to use these microlocal tools to show connections between physics, i.e. analysis, and geometry. So, thank you. Yes. So to make the statement really precise, we would have to, you have to assume, for example, just one boundary condition. I mean, we have results for we have a sort of a smattering of results for different contexts, and we would also assume, say, the same Euler characteristic. But then because the Euler characteristic just like goes down, right? For example, if we take the Dirichlet boundary condition, then any connected domain with no holes, with corners, is not isospectral to any smoothly bounded domain with or without holes, for instance. Yeah. I ate it up with the Euler characteristic. Because if you could write this expression equivalently with the curvature of the interior, well, that's going to be 0 because we're in the plane, and then the curvature of the boundary. But this is a little bit simpler.
Other questions?
What happens with cusps? Or like, what makes that different?
Well, for instance, I don't know what the angles would be, and I don't know. This is actually something that, yeah, and I'm not familiar with the local model we would use there, but Mehmet and I talked to Boris Wertmann, who seemed to think that we could address cusps. So this is tentatively something we will do in the future. Yeah. Because as long as we have a good local model, it should work in the exact same way. Should.
Could you say precisely what is the Rowlett parameter? So for instance, for the Neumann boundary condition, it would be 0, and for Dirichlet, it would be infinity.
And otherwise, it can just be a smooth function. Yeah.
What I find surprising is that this Rowlett contribution has a different order in time than the Dirichlet and Neumann.
Yes, it comes later. So it's easiest to see for a half space because you can write it down explicitly, and I could show you the expression and maybe explain it a little better. But the Robin heat kernel is the first order with the T denominator power is the same as Neumann. So it's this guy with the plus, and then the next term has a square root T. And that's sort of why. Yeah. It's actually really convenient because, for example, for like a sector, if I have Robin boundary condition, I can't write down the heat kernel. Like, I don't have an explicit expression. So it's very convenient that the leading order, I can cheat and use Neumann instead. Yeah.
At this level here of expansion, can you, by covariant theorem, can you correct the first term of the Wien expansion? Why can't you see the too far? How is the remainder too big to detect these things in the Wien function?
It's my understanding that I don't know, I could be wrong, but as far as I understand, I only really know how to use the heat trace expansion to get like one term in Weyl. I don't know how to use it to get anything beyond that. And I sort of think that it doesn't work. Something like, yeah.
Can you offer a little bit more insight into the like the physical interpretation, because you have area, which is like the length squared, and then you have the length, and then you have some dimensional quantities all mixed within one formula. But then that corresponds to different, the scaling with respect to time also changes with
I roughly think of it as like when you integrate, you're sort of adding up the heat, maybe. And so like first you sort of get like the area. And then if you have, for example, with Dirichlet, you get a minus in the next term. And so then you think of it as like, but you're losing, because Dirichlet, the boundary is 0. So you've got a minus sign because you're like losing it out there. But if you have a Neumann, you get a plus, and you think of Neumann boundary condition, well, actually it really means that is insulated. And so with the Neumann boundary condition, it's sort of trapping it. And then beyond that, I have no idea.
Can you also tell then, I guess, from this that all of the angles, like you detected one angle as the irrational
I don't really understand.
So, like, if you have just a polygon, for example, and you want to figure out if it's a rational polygon or an irrational polygon, then can you just, from the spectrum, can you figure that out?
I don't know.
Using this, I mean, one of the sums on the right.
Maybe. We could try.